Good morning. Yeah, you can see my screen. I wanted to just go over problem 6. Uh, I started looking at it myself so I could check your solutions, and it turns out it's pretty hard, or it's at least takes a lot of trial and error. You've got to go down different roads, and they don't always work out. Um, so you got to try different things, and then the pattern does not jump out at you right away. At least I haven't noticed. Well, some it kind of does, but then it's false confidence. So I thought I'd go through sort of how I was approaching these and things that I thought I saw along the way, and then issues with those things, and then trying to solve those issues, um, and where I'm at right now because I'm not done with it. But I thought I'd share my journey so far, just to sort of show you guys that this is how you solve the problems. There isn't a trick to this, really. Well, I mean, there may be, but you got to figure it out by guessing and trying. So anyway, here's 2 points, and it really doesn't matter where I put the 2 points. You know, if I put a point here with that one there, it would still cut the board into two pieces, as you can see here. I've got a line, and it cuts the circle into two pieces. So the problem was, you place any number of points in any way along the edge of a circular board, and then draw the lines in between every possible pair of points. You would call that a spaghetti network if you're talking about the graph of nodes being connected. If everything has a connection to everything else, you would draw all those lines. You're forcing these dots to be on the edge of a circle. How many sections do you cut the circle into? Maximum. With that number of points. So with 2, it always cuts the board into 2 sections. They don't have to be even sections, but I started with symmetry. I started arranging them symmetrically around the circle. So here's 2. You make one connection and 2 sections of the board. So that's what was I doing? Oh yeah. Well, I'll get to those numbers later, I guess. And then I did 3. You can already see what I'm doing with the way I'm coloring it, so I guess I'm sort of getting ahead of myself. At first I was just drawing these on a piece of paper. I can show you the paper if I can find the page. I did this on a couple different occasions, so this kind of spread out throughout my book. I don't know where it is. So there's some, and I don't know if you can see that, but I had all these little circles. My big ones, I drew them bigger when I had more points, and I was counting all the sections. I don't know, here's simpler ones. I don't know what I was doodling. And counting certain things. That was one page. I think I had more pages. I made a little table like I suggest you do. And in this case, I think I had the number of points, the number of sections. I don't know, what does that say? Oh, well, I'll get to that. I'll get to these other things that I'm counting. But one of the ones I was counting was how many diagonals, and I can explain what a diagonal is in a second, and the number of crossings. So that was, that kind of led me, that's kind of a, I didn't need to do all that, and it kind of isn't helping me get the answer, but it keyed me into my new strategy, which I think will get me there. But right now the pattern hasn't jumped out at me. I also did more paying attention to how many how the diagonals are drawn, think of it as a polygon, a regular polygon. If you draw the diagonals of a polygon, I did it in a particular way, starting from one vertex. I did all the diagonals, and then I did another one, and then another one. And as you count in that way, you can establish some patterns. And so then I guess I wanted to be more clear. So at some point I got to where I wanted to not make them symmetrical, so not make them perfectly regular convex polygons, because I realized that there was a difference when you had the polygons and when you didn't. And I wanted bigger numbers. I wanted to see what the more points. I wanted to see that pattern. So I eventually switched over to this graphics editor so I could have a clean, precise situation or thing to look at and play with. And I can make a couple of these so you can see how I was going about it. I started coloring them too. But so here's with 2 points, here's with 3 points. And if you connect them, that's the only way you can connect them. If I'll do another little circle. Well, I'll just duplicate this, I guess. I'm going to get rid of the colors. And I can, if I click these, I can sort of create a new arrangement for a triangle. I gotta like double click it. And then maybe so I can put my points in different places, and if I draw the lines between them, it's still a triangle. As long as they're distinct points, I can only cut it into 1, 2, 3, and 4 different sections. And no matter how I arrange my 3 points, I'm going to have 4 separate sections of the board. So they don't have to be symmetric. The question is, what's the maximum number of sections you can cut the board into? 4 is similar. You draw the lines between the points, but now, so I guess we can talk about, we have diagonals now when you have 4 points. So what is a diagonal? A diagonal, well, a polygon, you have vertices. In a vertex you have points along the edge, and they're adjoined. And in fact, this is every connection you can make between every possible pair. This connects to that, this connects to that, they connect to each other. That's all you can do. There are no diagonals because points are adjacent when they're one away. A connection to a non-adjacent point is a diagonal, and there's no non-adjacent point to any one of these points in this graph, so there are no diagonals. In this case though, if you think of this, I usually start at the top when I think about it. That one has the 2 adjacents, but there's 1 diagonal, so you can connect it. So you have a diagonal there, and then a diagonal can be drawn connecting these 2. And you can make an ugly looking little box, a little quadrilateral on the edge with the points on the edge of this circle. It's still going to make a little quadrilateral with diagonals, no matter how you place them. So with 4, you are going to have 8 sections, no matter how you arrange the 4. So we went from having 2 sections, no matter how you arrange the 2, 4 sections, no matter how many ways you arrange the 3 points, 8 sections, no matter how many ways you arrange the 4 points, and now for 5 points, we have a different situation. Well, sort of. With 5 points, I can make it symmetrical, and I can look at it that way. I don't think I can do any better than that. So you'll see I can have 1, 2, 3, 4, 5 of these red spots, 5 of these pentagonal spots or triangles, 5 of these triangles in the star, and then a pentagon in the middle, one lone pentagon. So kind of similar to this one. So I'm seeing patterns already. I'm seeing, well, if I have 3 points, I'll have 3 sections, 3 sections, and a thing in the middle. Okay, odd number 3. With 4, I have 4 of these and 4 of those. No middle spot, no extra bit. So 1 set of 3 and an extra bit, 2 sets of 4, no extra bit. And that's what I was sort of looking at. 1 set of 3, 1 extra, that makes 4. 2 sets of 4, no extra, that makes 8. So I was starting to try to, I thought I saw a pattern. With 5, I now have 3 sets of 5 and an extra. Ooh, that's my pattern, right? So I keep getting an extra set of however many points I have. So 1 set of 3, or here I had 1 set of 2, no extra, 1 set of 3, an extra, 2 sets of 4, no extra, 3 sets of 5, 1 extra. So that's looking pretty good. And again, no matter how I arrange that, I can't get any more pieces. That's the max. So it looks like symmetrical's good. But then I get to 6. And when I draw 6 symmetrically, I see I get 6 of these outer pieces, 6 of these pieces, 6 of these pieces, and 6 of these pieces, and 6 of these pieces. So I have 1, 2, 3, 4, 5, not 4, like I might expect. I have 5 sets of 6, and I have no middle piece. So I have 30. Not exactly my pattern. I am maybe seeing an alternating between how many extra pieces I have in the middle, nothing in the middle, 1 extra piece in the middle, nothing in the middle, an extra piece in the middle. That seems to be a pattern. But the top numbers, a little bit different. 1, 1, 2, 3, 5. Well, now I'm aware of some sequences of numbers, and actually I think we're going to look at some sequences of the numbers at the end of this year, because I think it'd be good for you guys, especially with this sort of problem-solving thing. You get sequences of numbers when you're trying to find patterns, so to be familiar with some sequences of numbers, I recognize this sequence of numbers. It's called the Fibonacci series. And the Fibonacci series, I should look it up on Wikipedia for you. Let me see here if I can do that. Fibonacci numbers or sequence. Oh, that's a nice little representation of it. It's a sequence of numbers that represents this. It's not really looking good on your window, is it? Let me see if I can. do this. So you have a pair of rabbits, and they're too young to reproduce. So you have one pair in your first generation. In your next generation, you have that same pair, but they're now mature, and I don't know why they're colored like that, but they're able to reproduce. So in the next generation, they will have offspring, and this is just a model. Don't think about it too hard. But if then they have offspring, and they're not dead, so they don't die ever. So they're still able to reproduce for the next generation. But their offspring are too young, and they're not able to reproduce. So how many the population are in each generation in terms of pairs is one pair, two pairs, then they reproduce again, the young grow up, and they remain. So now there's 3 pairs. The ones that just grew up are now old enough to reproduce. I can't really. Does that help you? So the young that just grew up, they now reproduce themselves and continue. The new young group grows up, and the original mature group reproduces it yet again and continues, and then that continues. And the way it works out is the mature pairs are equal to all the pairs of rabbits from the previous generation. So in the last generation there was 1, so the mature is equal to 1. In the last generation there was 1, so the mature is equal to 1. In the last generation there were 2 pairs, so the number of matures are 2. The matures are always the same as that before. The offspring are always the same as the ones that were there a step back from that. So the way the sequence generates itself is you take the last 2 generations, add them, and that's how many rabbits will be in, how many pairs will be in that generation. So you start with 1, and then 1, and then 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, and that's the sequence of numbers. It's supposed to represent biological growth in some way. But that's the Fibonacci sequence of numbers. It's pretty famous. But when you see, and it's famous because it's called a recursive definition of numbers. The sequence of numbers is defined based on the starting values, 0 and 1, and then basically you just add the 2 to make the next one. So 0 and 1 make 1, 1 and 1 make 2, 1 and 2 make 3, and it keeps referring to its previous value for its current value. So that's called recursive. It's defined based on itself. So the way they write that is like f n plus 1, the next one, is equal to the current one plus the past one. So it's a thing that sort of, f is defined based on what f was, it's sort of, that's what they mean by recursive. It's sort of in its own definition. Or you gotta sort of apply repeatedly to get to it, the last one. So these are the Fibonacci sequence, if I add it right. I just did that. And that's sort of what I'm seeing in the number of sets of size, however many points there are. So there's one set, when you have 1 point, there's no pairs. It doesn't cut the board. So with 1, it would be 0. With 2, you have 1 pair of 2, 1 set of 2. With 3, you have 1 set of 3, so 1, 1. With 4, you have 2 sets of 4, so 1, 1, 2. With 5, you have 3 sets of 5, so that's 0, 1, 1, 2, 3, 5. So I'm starting to see a pattern there. I don't know necessarily why that pattern's showing up there, but the Fibonacci numbers show up in weird places all the time. I wish I knew better why. There's probably a reason why they show up in certain places, but I'm seeing them. And this other number was pretty easy. It's just 0, 1, 0, 1, 0. It's just alternating. So it didn't go 1, 2, 3, 4, but it is starting to look like the Fibonacci sequence and an alternating number. So that looks like it could be the formula. But then something ruined that. If you mess it up, if you break the symmetry, you can get it so that there's another section in the middle, which you couldn't do before 6. Before 6, you can arrange the points any way you want and make an ugly little shape. It would basically be a transformed squish version of whatever you're doing before, a quadrilateral, a triangle, a star with a pentagon. It'll look weird, but it would cut the same number of sections no matter how you arrange them until 6. Now, if you arrange them symmetrically, you get 30 squares, but if you don't, you get 31. So that little alternator, that little 0, 1, 0, 1, is actually 1 again. If you're thinking of the extra, if you break the symmetry, and the question did ask, what's the maximum number of sections you can make with any given number of points? So now my pattern is buckling it again. So okay, let's go to 7. Well, the Fibonacci thing seems to be working. 5 plus 3 would be 8. So for 7, are there 8? So I colored them all differently. So there's 8. There's 7 reds, 7 orange, 7 yellow, 7 blue, 7 green, 7 darker blue, 7 purple, 7 pink, and then a standalone red again. So I have 1, 2, 3, 4, 5, 6, 7, 8. 8 sets of 7. Good. Fibonacci sequence is holding. Back to a single guy in the middle. Okay. I went ahead and tried to mess it up. And I kind of messed with it. And it was the same. I couldn't mess it up and get any more pieces. I still have 7 of the red, even that little one. I still have 7 of the orange, 7 of the yellow, 7 of the light blue, 7 of the green, 7 of the dark blue, 7 of the purple, 7 of these pink, and yeah, it's hard to see, but there's a little piece there. There's a 7th piece of the pink. That actually hints at something that I've discovered. And 1 standalone piece in the middle. It's no longer 7-sided. It's like 4-sided, but still the same number of sections. So okay, so that means 57. Because 7 times, you have 8 sets of 7, that's 56, plus the one in the middle, 57. Okay, 8. Pretty. So the next number in the Fibonacci sequence, 5 plus 8, is 13. So when I did the 8, I colored all the sections differently. I have 8 of the red, 8 of the orange, 8 of this yellow, 8 of the green, 8 of the mint, 8 of the lime, 8 of the light blue, 8 of the dark blue, 8 of the purple, 8 of this other purple, violet, and 8 of the pink. So I actually have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have 11 sets of 8 with no extra guy in the middle. So Fibonacci sequence just collapsed. We do not have the Fibonacci sequence anymore. Okay, what if I mess it up? What if I break the symmetry? It did have an effect on 6. It didn't have an effect on 7. Maybe there's something with odd and even. So I'm going to mess it up for 8. And it definitely did have an effect. I will just show you. I guess I'll try to show them both. So I still have 8 of the red. I have 8 of the orange. I have 8 of the yellow as before, 8 of the lime, 8 of the green, 8 of the grass color, 8 of the light blue, 8 of the dark blue, 8 of the purple. I guess the colors are a little bit off from what I did before. But I now have not 8 of these like I did here, but I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Can't miss that little guy. He's there. They don't cross at the same place, actually. So not 8, like I did here. I have now 16. And so I've got a whole extra 8. And in the middle, instead of having 8 things like I did over here, I now have 1, 2, 3, 4, 5, 6, 7, 8. I think I'm not sure if I got that little guy. But there's 8 still, as there were. But now there's things inside of it. There's 3. So there's an extra 3, which wasn't there before. So I got an extra 8 and an extra 3 by making them not symmetrically positioned. I'm not sure if that's the best I can do. I think it is. I think that's the best I can do because I've been thinking about it. So I got an extra set of 8, and then I got a spare 3, not a spare 1. So that means I now have 99, I believe, sections of the board with 8 dots. So not 13. So it's not the Fibonacci sequence, even though it was for the longest time. I'm not sure if I can bring that back. I don't think I can. And that little alternator, that's not what I was expecting. So it completely messed up my... I thought I had generalized it, and I was going to write a formula. I thought this would be the Fibonacci number. This would be a little alternator, but nope, I got it wrong. So I was questioning. I can break the symmetry. It seems like on the even numbered ones, not the odd number ones. Notice the odd number ones have a lone guy in the middle. The odd number ones I can't get extra pieces out of, it seems, by breaking the symmetry. But the even number ones, at least so far, I haven't checked them up until larger numbers. Maybe you can with odds. I haven't seen it yet. I don't think so. I'll explain why in a bit. But the odds have a thing in the middle, not a set of 5, a lone thing. And you can't, as far as I know right now, you can't get more by rearranging the dots. You can't get more sections. The evens, there's a collection at the middle. There's a crossing, there's a point, and there's a set of however many side dots there are. There's a set of that many at the center when it's symmetric. And if you break the symmetry, you can get some extra pieces out of it. Here I got 1 extra piece. On 8, I got 11 extra pieces by breaking the symmetry, and I think that's as good as I can get. So I thought I was getting it, but that completely broke down. And I wasn't sure why. So what I realized was, if you look at the 6, okay, I messed up the symmetry, and I got an extra piece where? In the middle. Okay, why the middle? Well, notice every crossing of the diagonals. How many lines are crossing? What I did in this thing, I'll explain that now, this thing, I was counting D's and X's, I think. I don't know if you can see that. I'm not sure what I wrote. But I was counting how many diagonals there were, and then how many diagonal crossings there were. Thinking that, okay, the diagonals will cut the board, and when the diagonals cross each other, that will further make sections. So if I can find patterns in those numbers, I should be able to come up with how the number of points is related to the number of sections that I can get maximum. But look at this one in the middle. It's 3 lines crossing. And what I realized was, I did it up here, is that if you have 3 lines crossing, if you move one, like so, they're the crossing, and there's just 1, 2, 3, 4, 5, 6 sections. But if you move it, on the outside, you still have 1, 2, 3, 4, 5, 6 sections, but now you have this triangle in the middle. Instead of having the intersection of this line with that line at the same place as this line with that line, you can take this one crossing and turn it into 1, 2, 3 crossings and enclose a region, a new region. So wherever 3 lines cross at the same place, not 2, you can, by breaking the symmetry and changing where the lines go, you can turn that into 1 extra section. So that's why with this 6-sided, you have 3 lines crossing here. So I can get 1 extra piece out of that. So that kind of explains that. I also played around with, what if I have 4 lines? Well, I could do something like that. And I got like a little Star Trek insignia, little arrow, like a little paper plane or something. I did that over here, and I can if I have 4 lines crossing, I could get 3 extra sections, and I solved that with the 8. Here, the middle can be explained because I have 1, 2, 3, 4 lines crossing, and I was able to get an ugly looking little paper airplane, a tiny little wing over here, but 3 extra sections from the middle. Well, I did it again, and I started highlighting, I started circling the intersections where more than 2 lines crossed. So here was a set of, here's 3 lines crossing. I can get an extra from that. With 7 points, there's no, you can call these a degenerate crossing, or there's more than one crossing happening there. It's hiding basically how many crossings there are because they're overlapping. But if you can get them to not overlap by breaking the symmetry, you can maximize the sections. I then went up to 9 and 10. Wait, that's 6. This is 7. That's 8. So with 8, I had 8 places with 3 lines crossing, so I can get 1 extra out of each of those, and you saw that I did. I got 8 extra pieces. So these 8 became 16. And then where the 4 lines were crossing, I got 3 extra. So that's what I did there. And then I did 9. And I looked and looked, and it doesn't appear that there are any overlapping crossings. It looks like they're all just one-to-one, one line crossing another line, no third or fourth. So I think that's the maximum I can get. So 17 sets of 9 plus 1 extra guy. And then I did it for 10. And there were 20 places where 3 lines crossed, as far as I could count. So I can get 1 extra from each of those. So that's 20 extra spaces if I just mess it up. And in the middle, I have 1, 2, well, let me start with this one. 1, 2, 3, 4, 5 lines crossing. As best as I could figure, with 5 lines, I thought I could get 6 new sections. With 6, I thought I could get 10. I don't know. I'd have to double check that. But this is where I'm at right now. So 24 sections of 10. Then I have 20 places where I should be able to get an extra square. And I've got 1 place where I should be able to get 6 extra squares. So I think 266 for 10, 154 for 9. I don't have it as a pattern yet, so I'm going to look at that longer. But I think I'm starting to get it. But I don't have a formula. But I don't know. So I just wanted to wrap that up just by going over the process. Start small, work up systematically, look for patterns. And I think the point of this problem was that you will see patterns that will break down sometimes. That's very common. It's very weird. But what the real goal here is to not just see the pattern in the numbers, not just be oh, well, the next number is this and the next number is that. I mean, that's good, that's great. But what's the real challenge and the real understanding is understanding why, where it's coming from. Like it's because the crossings are overlapping, or there's multiple crossings overlapping here. So I'm going to keep looking at this later, and I'm kind of done drawing shapes right now. But and that's the way you should do these. Chip away at it, keep notes, like don't lose where you're at, don't lose what your progress is. So I was making records of how many diagonals, how many crossings from this vertex. There's, if you go through, I can draw 3 lines. Imagine they're unconnected. So from here I'm drawing diagonals. I can draw these 3. So no crossings. But now that I put those 3 down, I can put 3 here, and I'll cross 1, 2, 3, 1, 2, 1. So I'm crossing the 3 originals. So I got 3, then 2, then 1 crossings. And then from here I'll get 3 crossings, then 2. Then from here I'll get 3 crossings. So a total of 30 crossings, I guess. Is that right? 9, 10, 11, 12, 13, 14. No, 14. I think I don't know what I'm doing here. So I was counting how many crossings. And that's when I realized that what should have been multiple crossings counted as 1 when they were symmetric. Crossings, this X and this X overlapped, so it was 1 place instead of multiple places of crossing. Just like here. Whoops. It looks like 1 crossing, but it should be 3. If you rearrange it, it could be 3. So how this pattern of overlapping crossings develops, first, so by 6 you get 1 of these little weird issues, and it's not too bad. You just get 1 extra from that if you rearrange it. Then you get a set of them, and now this one has 4 lines instead of 3. These are 3s. That's a 3 in terms of how many lines are crossing. That's a 4 surrounded by 8 3s. And then on the 10, you now have, unless I'm missing some, I don't think I am. I think that's it. I now have 2 sets of 10 3s. They're 3s. And in the middle is a 5. So I think I'm seeing a pattern, but and if I know for each one of these I can get 1 extra, for each one of those I can get 6 extra, for each one of these I can get 3 extra. I'm getting closer to a formula, but I'm not there yet, and it's a challenging problem. So I just wanted you guys to see that how this goes. It's a challenge for me, but and it's time consuming. You can't just look at it and be like, oh, it's this. You really have to work at it, and you will come up with ideas, and they will look good, and it won't always be right, but you got to persevere. Anyway, this is an unfinished state, so you guys can still see if you can do something with it, but also this one was a lot more involved than I thought it was. I thought we were just going to have problems that, exemplified the method of, start small with examples, work up systematically to the larger one, and then detect the pattern and try to describe the pattern. This one was a much more challenging than just that. You do have to do all that, but it involves failure and trying again. So it's a very good lesson, but not a quick one. So anyway, I hope that is somewhat interesting to you and that you see sort of my process, and I hope that helps you if you were having trouble with this one. When I thought I had it with the Fibonacci sequence, I was coming up with formulas way too premature, because as I went down, I saw that broke down. I don't know if I can salvage that with all these extras I'm getting, but I don't know. I'm going to chip away at this one later, but anyway, these are pretty rich problems, so I hope you are trying them and exploring them. It's this, it's not about a right answer, a wrong answer. What is the answer? It's I want to see you guys doing this, working on solving the problem solving method. Anyway, so this is sort of, sorry for this one being particularly bad, but at the same time not super sorry. This is actually pretty good for that it is so bad. It's still interesting and doable, but I could definitely see you guys struggling with this. So I just want to maybe help or at least comment on it. So anyway, that's 45 minutes. You guys have a great weekend. I'll hopefully talk to you next week in some sort of meetings, but take care.